Let's see if we can draw the Lewis diagram for a nitrate anion. So a nitrate anion has one nitrogen and three oxygens, and it has a negative charge. I'll do that in another color. It has a negative charge. So pause this video and see if you can draw that, the Lewis structure for a nitrate anion. All right, well, we've done this many times. The first step is to just account for the valence electrons. Nitrogen has 5 valence electrons in its outer shell, and in that second shell, if it's a neutral free nitrogen atom. So we have 5 valence electrons there. Oxygen has 6 valence electrons. But if you have 3 oxygens, you're going to have 6 times 3. And so if you just add up the valence electrons, if these were free neutral atoms, you would get 5 plus 18, which is 23 valence electrons. Now, the next thing we have to keep in mind is this is an anion. This has a -1 charge right over here. So it's going to have one more extra electron, one more extra valence electron than you would expect if these were just free atoms that were neutral. So let's add 1 valence electron here. So that gets us to 24 valence electrons. And then the next step is let's try to actually draw this structure. And the way we do it is we try to pick the least electronegative atom that is not hydrogen to be the central atom. And in this case, it is nitrogen. It's to the left of oxygen in that second period. So let's put nitrogen in the center, right over there. And around it, let's put 3 oxygens. So 1, 2, 3 oxygens. Let's put a single bond between them. And so far, and let me do that in another color so we can account for it better. So I'll do them in purple. So far we have accounted for 2, 4, 6 valence electrons. So -6 valence electrons gets us to 18 valence electrons. The next step is we would try to allocate as many of these as possible to our terminal atoms, the oxygens over here, try to get them to a full octet. So let's do that. Each of these oxygens, they're already participating in one of these covalent bonds, so they already have 2 valence electrons hanging out. So let's see if we can give them each another 6 to get to 8. So 2, 4, 6, 2, 4, 6, and then 2, 4, and 6. And so just like that, we have allocated 18 valence electrons, 6, 12, 18. So -18 valence electrons. And we are now left with no further valence electrons to allocate. But let's see how our atoms are doing. We know the oxygens have a full octet, but the nitrogen only has 2, 4, 6 valence electrons hanging around. It would be great if there was a Lewis structure where we could have 8 valence electrons for that nitrogen. Well, one way to do that is to take one of these lone pairs from one of the oxygens and turn that into another covalent bond. So let's do that. So let me just erase this pair right over here. And I'm just going to turn that into another covalent bond. And this is looking pretty good. We have 8 valence electrons around each of the oxygens. And now we have 8 for the nitrogen, 2, 4, 6, 8. And we have to remind ourselves that this is an anion. It has a -1 charge. So to finish the Lewis diagram, we would just put that negative charge there. And this is all well and good. But if this was the only way that nitrate existed, when we observed nitrate anions in the world, we would expect to see 1 shorter bond and 2 longer bonds. And we would expect one of the bonds to have a different energy than the other 2. But in the real world, we don't see that. We see that all of the bonds actually have the same length, and they actually have the same energy. And so the interesting question is, why is that? And one thing that you might appreciate is, when I took that lone pair to create this covalent bond, I could have done it with that top oxygen, I could have done it with this bottom left oxygen, or I could have done it with that bottom right oxygen. And so there's actually 3 valid Lewis structures that we could have had. Not only could we have had this Lewis structure, we could have had this one. And I'll draw it all in yellow to save us some time, where you have this nitrogen. It has a single bond with that top oxygen. And so that top oxygen still has 6 electrons in lone pairs. And maybe it forms a double bond with the bottom left oxygen. So this bottom left oxygen only has 2 lone pairs. One of them would have gone to form the double bond. And then this oxygen would look the same. So what I am drawing here is another valid Lewis structure, or the double bond might have formed with this bottom right oxygen. So let me draw that. So another valid Lewis structure could look like this. So nitrogen bonded to that oxygen has 3 lone pairs. This oxygen also has 3 lone pairs. And now this one has the double bond and only has 2 lone pairs. And whenever we see a situation where we have 3 valid Lewis structures, we call this resonance. 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 And we'll put an arrow, these two-way arrows, between these structures. And when you hear the word resonance, it sometimes conjures up this image that you're bouncing back, you're resonating between these structures. But that's actually not right. What the right way to think about it is, these different ways of visualizing the nitrate, these contribute to a resonance hybrid, which is really the true way that the nitrate exists. And so if we wanted to draw a resonance hybrid, it would look like this. You have the nitrogen in the center. You have your oxygens, 1, 2, 3. I can draw our first covalent bond like that. And then you would show the bond between nitrogen and each of these oxygens are a hybrid between someplace between a single bond and a double bond. And so instead of just one of them having the double bond and the other two having single bonds, they're all somewhere in between. And so maybe you draw a dotted line, something like that, to show what the reality is that you actually have 3 bonds that are someplace in between a single and a double bond, because the electrons in this molecule are delocalized throughout. And of course, you want to make sure, you always want to make sure that people recognize that this is an anion. So this is the idea of resonance. You have multiple valid Lewis structures. They all contribute to a resonance hybrid, which is actually what we observe. We're not just bouncing between these different structures. The actual observation will be a hybrid of the 3. Now, what we just drew here, these 3 are all equivalent, but in certain cases, and we'll see this in future videos, you don't have equivalent structures, and some of them might contribute more to the resonance hybrid than others, but we'll see that in future videos.